in Dartmouth College. So working one time in ice geology, ice structure interaction, and very interesting topic, ice friction. Yeah.
How much time?
1 hour. So this question. This question.
1 hour.
1 hour.
1 hour.
Yeah.
You can leave now if you wish. Thank you. Well, firstly, I would like to thank Alexei and the organizers for inviting me here. I hope you won't be disappointed. What I want to speak about is, as you see, friction of sea ice. Why do we care? Well, of course, you understand why we care about sea ice. But why do we care about friction? Well, it turns out that friction is really a fundamental process in sea ice mechanics, at least a variety of sea ice mechanics. And let me illustrate, if I may, before I get on with the subject. What you're seeing here is an image taken from a twin otter. We were flying about 1,000, 1,200 feet over the Arctic, Beaufort Sea some years ago. You see a crack running horizontal across the image, and there's a bit of displacement across the crack. As you can see, left lateral sliding, at least as seen from above, probably right lateral if you're a fish. So you see the displacement, and associated with the displacement, if I can just put it here, it's a bit of rubble has been created. We might call that a shear ridge as a result of the shearing, the left lateral sliding. What's interesting to note is that the sliding that had occurred, at least we think it had occurred by the time we took the image, it was intermittent. There were episodes of sliding. And how you determine that is if you look at the leads on either side, the left and the right, you see different thicknesses of ice. Ice had opened, more ice lead had formed, more ice had formed, it opened again. So those shades of gray, dark mean that the sliding had occurred in a rather stop-start fashion. And so if we ask, well, what's going on here? We know there's static as well as dynamic/kinetic friction at play, which is what I want to address. Other examples of sliding. Here is an image, Devent's meteorological satellite image, goes back 30 years. You're seeing an alignment of leads. An alignment of leads oriented, it seems, not random. And if one looks closely, there's evidence perhaps in that set of leads of inclined cracks from the tips of which extend other cracks, other leads. And we would interpret that process within the classical, going back even to Griffiths, 1920, within a sliding crack phenomenon, sliding along a parent inclined crack, generating tensile stresses at the tip, which are relieved through the development of extensile cracks running along a direction of loading compression. So the hypothesis Bill Hibbler and I produced at that time was that this is a frictional sliding type process, and that we're seeing here is evidence of a failure under a compressive state of stress. Other evidence of sliding, if we look again, here's some Landsat 7 images of the Arctic ice cover. On the left, I show basically what we might call a linear kinematic fault. At least Ron Kwok speaks of them as linear kinematic features. But what you want to notice about the feature is there was evidence of sliding. See these rhomboids everywhere, there's rhomboid type features. And again, what I'm showing here, this is a right lateral sliding to create that rhomboid. And if one proceeds along that particular LKF, a series of these sliding features. If you look to the right, you see a set of intersecting linear kinematic features, and I call them Coulombic shear faults. The implication here is that these features are being created by a compressive, far-field, wind-originated compressive stress. And here they're intersecting, two intersecting type features. And from the theory of brittle compressive failure, what we're seeing, this pair of intersecting features can be described solely in terms of the coefficient of friction. These are conjugate faults, we interpret them to be. Conjugate faults, which from the theory tells us that the angle of intersection between the pair, the angle of intersection is governed solely by the coefficient of kinetic friction, which if you take the angle in this case, work it out, you get a coefficient of friction of 0.9. That will come out again for the measurements that I will show you in a moment. Other evidence of sliding, of course, finger rafting, no question there about ice sliding over itself. And further evidence, we have here the formation of a ridge in the Baltic Sea, ice blocks from Tukuri's group, etc., sliding over each other, and that process of sliding, the friction resisting the sliding, is what I understand from their group to be an important factor in the building of the ridge. Again, friction. Here we have friction perhaps expressed a little more mathematically, since this is the conference on mathematics, in terms of what is it that limits the brittle compressive failure of ice when pushed against any obstacle, or even when pushed itself. And I'm not going to show you the details here, but the modeling that we have done has been able to, I think, at least at some level, account for the failure envelope in terms of a frictional sliding mechanism. I won't go into the details. If you note the references, you can find them, but the essence of the mechanism is somewhat a variation on the theme going all the way back to Griffith, brought in forward with friction. A series of sliding along some parent inclined cracks, creating in the process stresses which lead to the creation of a set of slender, rather, columns fixed on one end, free on the other, and additional frictional sliding along the free end causes the first comb, tooth in the comb, if you wish, we call it a comb crack mechanism, to fail. And if one makes an analysis, ends up with an expression of this, and I don't expect you to read all of that, but the important point, the important element in the model is the coefficient of friction. There it is. There are no parameters that are adjustable here. Each of them can be independently measured. I won't go through them, but the friction coefficient appears yet again. And here it is, a non-dimensional plot of the brittle compressive failure stress versus a degree of confinement. The line on the plot is the theory. The points in the plot are data obtained not just from ice, but from other geophysical materials. The model is not limited to ice. Again, friction. And here, related to that theme, is again an explanation of the transition from ductile behavior when ice is deformed rather slowly to brittle behavior when compressed rather rapidly. Again, in terms of that same model, but this time one simply invokes at the tip, oops, where are we here? One simply invokes at the tip of the secondary cracks a creep zone, which if large enough, blunts the crack so that the overall behavior of the material is ductile, creepy, whereas if that creep zone is smaller than the elastic strain zone, fracture continues, the crack grows, the material exhibits brittle behavior, and then the transition is when the creep zone size and the fracture zone size are about the same. There's a competition between creep and fracture, and that too is manifested in terms of a model which again incorporates the friction coefficient as well as some parameters associated with creep and fracture propagation. So again, friction continues to show itself. One more time, here's a failure envelope for sea ice. A failure envelope, brittle compressive failure envelope, showing measurements from the laboratory on samples that have been taken from the first year sea ice cover, and also measurements made in the field on ice. And the point to note from these envelopes is that in each case, at least in the laboratory, of course, one knows what the confining stress is and can measure the failure stress. One obtains the envelope of failure. In the field, one simply has all kinds of points, and you don't know what is actually going on when you're measuring the stress. But if you put the envelope, if you put a limit on the field of points measured, then you obtain slope, a failure, if you wish, a failure envelope, the slope of which is almost identical to the slope of the envelope measured on the small scale in the laboratory. If you note the numbers here, the strengths in the laboratory on the megapascal scale, in the field they're kilopascal scale, 3 orders of magnitude difference. And I believe that's simply a reflection of the fact that in the field, stress concentrators are 1,000,000 times larger than in the laboratory. But other than that, it looks rather similar, the envelope. And again, what determines the slope of that envelope is nothing more than the coefficient of friction. That's the only factor that goes into determining the slope. And again, if you take the slopes, one ends up with a coefficient of friction of around 0.9. similar to that value one obtained from the conjugate faults. So there we are, elements of evidence, if you wish, of friction, frictional sliding. Why friction is important then in mechanics of sea ice, I hope, will be evident from that set of examples. So what's going on? I want to talk about then the character, the nature of friction, at least as best we understand it. Sea ice. I don't want to say much about sea ice. I think David Cole in his presentation, David, you're here, will tell us more about the structure of sea ice, but just so you know what it is we're dealing with. I look at ice as a material, and as a material, it has properties, and those properties are generally, as of all materials, reflected by the inner structure. What is the structure of sea ice? You see it here. Example, simply a columnar grain. It's a columnar grain material, a cube. You see the scale of the structure here. And if one looks a little more closely, of course, or asks, really, from what crystal structure is this ice made? It is a crystalline material, and ice under atmospheric conditions exhibits the hexagonal type of structure determined ice 1H. And I think you can see the character of the hexagon here. What's important here, what I'd like you to leave, is that although sea ice, as I will show you, contains not just freshwater ice, 95% by volume, there's a little bit of brine. But as I hope to show, the brine doesn't have much of an effect on the friction. So there we have it, and there's the example of the structure looking at a cross-section, horizontal and a vertical section. In both freshwater ice and saltwater ice form through the unidirectional solidification of water. The structures look very much the same on this scale, and you notice the hexagonal axis, the little yellow feature in the image. The hexagon typically is on its side in first-year sea ice, so-called S2 ice, but randomly oriented.
Maybe microphone.
Oh, can you hear me sitting back there?
Yeah.
You can. Oh, go ahead. Just a slight pause. So when I'm being fitted with batteries, which is carry on. So that's the structure. And when I'm talking about the friction later, I'm going to slide column against column sideways. So the columns are going to go sideways, as it would be perhaps in nature. Yeah? And if one looks a little more closely, then within each of the grains, you see a substructure. You see the brine pockets here. They're sub-millimeter in scale. And as well, if one looks even still more closely, we see those brine pockets. There's an alignment to them. They're not random. They tend to lie along the basal planes in that hexagonal unit cell. If we go more closely as well, one sees brine drainage channels. On a scale of about 10 centimeters, their presence, their effect, if any, is difficult to measure. Certainly there's an effect of them on tensile strength. But because of the scale, in the laboratory, it's hard to get samples that will incorporate a large enough set of brine channels to be representative. So often in laboratory measurements, brine channels are missing. They will be for the measurements I'm describing. So let's carry on. What are the coefficients of friction, kinetic, and static? And the kind of measurements I would describe have been done typically under what we term it double shear. The measurements in our own laboratory are in that way. Measurements in ice tanks by Peter Salmon's group have been done sort of in that way. In the field, they tend to be blocks sliding upon each other. We'll find that the measurements made under each of those conditions really reflect each other rather well. Not much difference, if any. So here are some static friction tests. Let's talk first about static. You remember in the image I first showed you, there was clearly some time where the ice was under load before it slid and it stopped again. So stop, start, stop, or slide, hold, slide tests are the first that we might want to describe. Slide, hold, slide, and here is ice both taken from the Beaufort Sea, ice from the Beaufort Sea, and freshwater ice. Again, for comparison, at temperatures that may be of interest, minus 10 to minus 30, and at sliding velocities here, 10 to the minus 6 on to 10 to the minus 4 meters per second, maybe higher than that in the field, but that's all right. And hold times, not very long in terms of nature, but a few hours. Takes a long time in the laboratory. And I'll show you a set of results typical of the whole. So what I ask you to imagine here is ice sliding on itself, stopping, under load for a period of time, and then sliding again. Stopping, under load for a greater period of time, sliding again. Ad infinitum, continuing, sliding, under that same load for still long periods of time, sliding again. And what you see in each instance is that while the load to cause sliding hasn't changed very much, regardless of how long the interval of holding was, the actual load to continue or to start sliding again, that is to initiate sliding, increases with increasing time of holding. So there's some kind of what we call static strengthening going on here. We're not the first to see that. That was seen by Leishman and others before us, and I'll show you their results. We see then, let's describe that coefficient of friction in terms of the shear stress divided by the normal stress acting across the sliding plane in the way people generally describe friction. And there's a characteristic behavior. If we see the results you're seeing here are the coefficient of friction as the log of the holding time for the 3 sliding speeds I mentioned a moment ago, 10 to the minus 6 on to 10 to the minus 4 per second. What you see, aside from an early stage, in fact, the early stage is rather important. If we look at the lowest speed, 10 to the minus 6 per second, then one sees there's a period of initiation where there is no evidence of any static strengthening. That the load to resume sliding was about the kinetic coefficient load, if you wish. Nothing happened until there was a threshold period beyond which you start to detect an effect. And at the higher speeds, that threshold time shortens to the point at 10 to the minus 4 you don't see it at all. It's probably shorter than the measurement time here. The strengthening can be described in a logarithmic fashion. If you want natural logs, that's fine, just change the coefficient. But there's a coefficient, so there's a log type plot, a log type behavior that's evident here. Little effect of salinity. And this is the key point, I think. Whether you're dealing with ice taken from the Beaufort Sea, which is in one case here, or ice simply grown in the laboratory, freshwater ice, which is the second case here, the data fall upon each other. All in here, there are 3 different rates, the fastest, the slowest, and you really can't tell the saltwater ice from the freshwater ice. Not only does salinity have a little effect, temperature doesn't have a very large effect either, curiously, at least over the range of temperature from about minus 10 to minus 30 degrees centigrade. A little effect, but we're not going to worry too much about that. What else? The agreement between laboratories, at least 2 laboratories here, I would say is good. Here's Leishman's results, taken a little before ours, placed upon results obtained at Dartmouth, and I think you can see that the similarity is a whole lot greater than the difference. So there's some universality in terms of this behavior, if you wish. So what's going on? What's going on to describe that, what we call static strengthening? What I ask you to imagine is what was imagined earlier by Bowden and Tabor, going back many, many years, where they consider the sliding interface not to be a mathematically flat interface, of course, but the interface to be characterized by asperities that protrude from the opposing interfaces, one then in contact with the other. And so it's contact mechanics here. What's happening at these points of contact? What is going on? And the first thing I want to ask is, well, what is the size of the contact area? That is, we denote it here by A sub 0. I think we can deduce that, or at least we did deduce it from the measurements. You see, what's happening is, during sliding, of course, during sliding there is contact, and during holding there is contact. So there is a total of 2 times that make up the holding time. We call that the interaction time, the time to slip or slide, plus the time to hold. The time to slip is just the size, the diameter of the asperity, divided by the velocity that's applied when sliding. And the time to hold, of course, is what one imposes in the experiment. In terms of making measurements through experiment, one can only begin to make measurements when the slip time is in fact less than the holding time, or put it the other way around, when the holding time is greater than the slip time. And therefore we assume that we can first detect static strengthening when these 2 times are equal. It tells us then, all right, we know the holding time for the threshold. You saw the threshold that had to be met before there was any measurement, detectable measurement. So if we set the 2 equal, it tells us that the size of the contact is given by that simple relationship, which, if you put in the numbers again, And here you see that threshold particularly clearly at the lowest speed of 10 to the minus 6. And I've listed here the threshold times for the different speeds. You come up with each case a contact diameter of about 30 micrometers, which tends to fall in the range of 10 to 100 micrometers that one often reads about in the literature on tribology as being the size of asperities. I didn't read that until after we'd come up with that result, so the result was obtained before reading that. It wasn't contrived. So, to understand what's going on then beyond that point, we think of an asperity, again in contact with its neighbor. I'm showing half a contact here, the other part above is not there. While holding, the asperity creeps. It shortens and it widens. As a result of widening, then there's greater contact area, and upon subsequent sliding, then the load or the shear stress required to continue sliding must go up. The greater the creep, the greater the area created, the greater the shear stress to be overcome to reenact sliding. And so the model here that I come up with, and I'm not giving you the details, although the reference is here if you so wish, we've envisaged the simplest possible creep law, power law creep, where the creep rate simply scales through the material's constant of stress to some power n. A better description might be a hyperbolic sine function, as Barnes, Tabor, and Walker taught us, or some other function, as others have shown. But it doesn't matter, I wanted the simplest. And there's the simplest relationship one can get. I'll describe it for you in terms of the hardness that the material exhibits. B is a parameter in the parabolic creep law. I can describe that if you're interested later. But what's the result? The idea is that once sliding then is re-imparted or imposed, then eventually the contacts must come apart. The failure, the coming apart, I believe, is a tensile fracture. For the sliding induces a tensile stress within the asperities, and the principal stresses are such that the fracture, the principal stress will be lining at some angle less than 45 degrees. Fracture occurs of that kind, we think. If we then put into the criterion simply the tensile strength of ice, and then one ends up with an expression of the kind you see here, and what you really want to know is it any good? Well, parameters, a variety of materials parameters are in that relationship, and one can see the power law creep relationship in terms of stress to the power n. We chose n equaling 3. Perhaps not a very good number, because as Barnes, Tabor, and Walker taught us so many years ago, that the n value increases with stress, particularly at stresses beyond an MPa. And we believe that the contact stresses are probably well beyond an MPa, but we use that number anyway for simplicity. We also use for the creep parameters for bulk ice. Well, is that the same parameter for an asperity that's 30 micrometers in diameter? We don't really know, but we have nothing else to go on, so that's what we use. You might wonder, well, surely the B value should be different for sea ice than it is for freshwater ice, because as everyone knows, sea ice creeps about 10 times more rapidly than freshwater ice, typically. But I would remind you that the asperities themselves are only about 30 microns, at least from this analysis. And if you remember that one of the images I showed earlier, the brine pockets are separated by a distance greater than that. And so it's likely, we think, that even in sea ice, the asperity is just a piece of freshwater ice sticking out from the surface. And so the B parameter for freshwater ice is probably appropriate for both cases. Other factors in here, we had to choose a hardness. So we used one. Barnes, Tabor, and Walker again do tell us that the hardness depends on the time of loading. Well, rather than making the thing more complicated than it need be, we just chose one value for hardness, just to start it off. A hardness value of 30 MPa, I think that's what we did here. A tensile strength of 6 megapascals, which is about the tensile strength of single crystals from Michel's work so many, many years ago. Putting it all together then, one ends up then with the relationship. Where do we have it? With this very simple relationship, that the coefficient of static friction as a function of holding time at minus 10 at a particular intermediate velocity of this one here is given by this dotted line. So there's the dotted line coming out from that model. The measurements are the points you see here. And there's a modest agreement, not perfect for sure, The model seems to underestimate a little bit the coefficient of friction, maybe by 10% or so. If you apply it to the highest speed, the model is going to underestimate the coefficient. If you apply it to the lower speed, it will overestimate the coefficient of friction. Possibly that's because of not using the correct n value, possibly because the b value must change. But the point here is that it's within a factor, perhaps 20-30% of the actual measured values. You may wonder, well, I don't see the logarithmic relationship in the time dependence here. One can get the logarithmic relationship if instead of the simplest power law relationship for creep, one uses an exponential relationship. We don't have to go into that. But the point here is, at least to a first approximation, there seems to be modest agreement, at least, between the model and observation. So much for static friction. Let's go on to kinetic friction. Again, I remind you, that if there were no sliding, there'd be no building up of rubble. And so I want to talk about low speed kinetic friction. And by low, I'm simply arbitrarily cutting it off at about 1 meter per second. We know from Aksonen and Kaunen and others that at sliding speeds beyond about 1 meter per second, the whole interface is water. It's melted. And we're getting into a hydrodynamic domain. I'm not talking about that. I want to limit my discussion here to low speed sliding. Characteristic of sliding at these lower speeds is stick slip. Whether it's measured in the laboratory, sliding across both smooth surfaces, rough surfaces, whether it's measured in an ice basin test for Peter Simon's group, whether it's measured on sliding blocks, by Sukharakov, Prochard, etc., even ice ridging and rafting seen in the field. It's all jerky. There's also this is a dynamic kind of instability we have in the stick slip process. I don't want to talk about it. I don't understand much about it, but it is a dynamic instability. What I will describe then is a kinetic coefficient of friction that's taken by the mean, if you wish, the mean sliding load divided by the normal load. What is the law? What law does the ice behave? I note here that sliding at these lower speeds under relatively low normal stresses, less than 100 kilopascals, maybe 200, obeys Coulomb's law, where the shear stress to cause sliding is directly proportional to the normal stress acting on the body. We've done experiments of a variety of normal stresses, and whether the temperature is lower than I'm showing here or higher, one tends to see that linear relationship. And the coefficient of kinetic friction, of course, is the coefficient multiplying the normal stress. But that's not what others see. At a higher normal stress, quite a lot higher, typically 5 to 250 megapascals, it's a nonlinear relationship between the shear stress and the normal stress. And you'll have two sets of results here, I get from Simon's group and Rist, and you see in those cases there's a different kind of relationship. I don't know what that means. Possibly under these higher normal loads, there are additional additional processes that are consuming energy. And these loads are high enough, certainly, to begin to initiate compressive failure. And one wonders whether there's a lot of compressive failure going on to lead to this non-linear behavior. I don't know, but it is different. So I will talk about the Coulomb's law type behavior in what I describe to follow. This behavior seen under the lower normal stresses. So moving forward then, set of results from fresh water ice sliding over itself slowly again at -10 blue, -10 is orange, -50 is blue. Behavior is similar in both cases. At lower sliding speeds, there's an increase in the coefficient of friction, and at higher speeds, a decrease in the coefficient of friction with sliding. Those coefficients here were taken not simply from the ratio of shear stress divided by normal stress, but they were taken from the slope of the shear stress normal stress curve. And that distinction is important. It's very important at low normal stresses. For if we take at low normal stresses the ratio solely of shear stress to the normal stress, and there happens to be an intercept in the Coulomb's law, then you're going to get a slope that's much greater than you would get from the tangent to the curve. And you could be misled by taking simply the ratio of those two stressors under low normal stresses. These are taken from the slope on the curve. So you see those two regimes, but they're not limited to freshwater ice on smooth surfaces. Here you see a set of data, coefficient of friction again along the vertical axis, and along the axis you see the velocity of sliding for both freshwater ice, and for sea ice. Both columnar ice, sea ice again, blocks taken from the Arctic, sliding across the columns of the kind I showed you. Minus 10 is one set of results, minus 40 is another. Don't worry about the difference. And don't worry about the different points here taken at different points on the sliding, whether at 2 millimeters, 3 millimeters, 8 millimeters. The point to note, again, two regimes, a rising branch at the lower speed, a decreasing branch at the higher speed. Both temperatures, both materials. And again, the similarity is much greater than the difference, one material to the other. The blue points here are meant to be the freshwater ice, smooth surfaces. Of course, the roughness, owing to a coulombic shear fault of the order of a millimeter, is going to raise the coefficient of friction somewhat, and that's why you see it somewhat higher. Dual behavior of the kind I just described is not limited to ice on ice. Barnes, Tabor, and Walker all those years ago in '71 showed us it also is characteristic, if you wish. Here we are. It's characteristic of ice sliding on granite, about the same temperature, of ice sliding on glass. There's a rising branch, a falling branch, a rising branch, a falling branch, in both cases. Okay, there's something general perhaps about this behavior. Indeed, even in the geophysical literature, certain minerals exhibit similar kinds of behavior when sliding over themselves. Something general here. Size, not a factor here. Measurements made in the laboratory are small pieces of ice, of course. Professor Zakharikov and Lawson did experiments in the field, blocks of ice, meter-sized blocks of ice. And I'm showing here their results, their results at somewhat higher velocities than were obtained in at least my laboratory. And I'm showing that my laboratory results, if I put them here, they're at lower speeds, or somewhere here, at least they fit on the curve that obtained in the field, sea ice blocks sliding over itself, whether top of block sliding on top, or side of block, or bottom sliding on bottom, doesn't matter too much. The other important observation made by Sir Gilacor and others is that the presence of seawater at the interface has little detectable effect on the resistance to sliding. One more time, good agreement between at least two groups here, showing data here from the laboratory of Ben Lishman, Peter Salmons and others, and again results from the Dartmouth group. Lishman's results obtained in an ice tank, meter-sized blocks of ice. Dartmouth results, small pieces of ice. Nevertheless, you're seeing here, again, similarity, which I think is much greater than any difference. There's again certain universality. Roughness, yes, as I alluded to a moment ago, coulombic shear faults, that is, rougher surfaces, do exhibit somewhat greater resistance to sliding than a smooth, that is, a micrometer-sized roughness type interface. But this dependence is not a strong dependence. Over orders of magnitude, 3 orders of magnitude, one gets the sense that the coefficient of friction is increasing by perhaps a factor of 2. That could be important, of course, for models, but the relationship is that the coefficient is scaling its roughness perhaps to the power 0.08. That's a fairly small dependence. You might ask, from the point of view of this meeting, the Arctic, snow, what effect does snow have on the resistance to sliding? It has an effect. But the coefficient of friction, at least at a speed of 10 to the minus 2 per second, somewhat higher, about a factor of 1.3, detected by Pritchett and others, who put blocks of ice sliding across a snow-covered surface of first-year level ice. So yes, there is an effect. But what about ice sliding against concrete and steel? And of course, those are the materials of which structures are made. Ice pushing against them, you ask, what are their character? Same thing. Now I'm showing here results obtained at higher velocities within this low speed regime by Saiki et al. And what you notice here is velocity weakening. Again, velocity weakening over the range of law. I don't know what they observed at lower, or I don't know about lower speeds because it didn't report them. But notice here again, the same kind of behavior I just showed you for ice sliding on ice. The upper curve here is the static coefficient of friction. The lower curve is the kinetic coefficient of friction. So in addition to noticing the velocity weakening, two other points are worth noting. Firstly, the coefficients here are significantly lower than the coefficient for ice on ice. Well, that shouldn't be a surprise to anybody because hard materials, and steel and concrete are harder than is ice. Hard materials typically have lower coefficient of friction than soft materials. So that's in keeping with what one generally knows about tribology. And secondly, here if you look, steel in fact has a lower coefficient than does concrete, for steel is indeed harder or stronger than concrete. And one more time, if you read their paper, they point out that the presence of seawater has little detectable effect on the coefficient of friction. Ice on ice, as Sergi's results show us, now as Saiki and al. Show us, the presence of water at the interface is not doing anything detectable, at least, to the coefficient of friction. So what's going on? Same question. 5 minutes. What we think is going on is the following. Again, we invoke the notion of asperities protruding from opposing interfaces. And again, the issue here is contact mechanics, asperities contacting each other. I'm going to describe three regimes, at least speak of two. I spoke about the velocity hardening, strengthening regime. I spoke about the velocity weakening regime, and I did not speak about the hydrodynamic regime, where again, velocity strengthening is evident, but of a different magnitude. So I want to speak about the slower region within our speed and the somewhat higher region within our low speed domain. So I'm arguing here that at low speeds, we're going to deal with basically creep behavior of asperities in contact. At higher speeds, I'm going to invoke the notion that the velocity is now high enough and the heat so generated through frictional sliding great enough to cause melting localized at certain asperities. Certain asperities will begin to melt. And at still higher speeds, more asperities will melt. Until finally one gets into the hydrodynamic region where all asperities have melted, there is a continuous layer of the water of interface and the physics changes. So first, a word or two about the low speed regime, which I call dry sliding, and then we'll get into dry wet, and I'll not talk about wet. Dry sliding. We're going to talk about basically thermally activated deformation of asperities in contact. That's just another word for creep. Creep deformation. So one more time we're asking, well, what's going on here? And we'll evoke the idea that within the sliding interface there is some kind of deformation zone. Barnes, Tabor, and Walker speak about a deformation zone in their experiments. They tell us it's about 100 micrometers. I'll put that number to work in a moment. So we say, well, let's imagine here, and let's define the coefficient of kinetic friction solely in terms of the shear stress, the critical shear stress to break away from an asperity, divided by the normal stress, pushing it all together. And the critical shear stress we know is a function of temperature and a function of the strain rate that the asperity is seeing. We know as well that the normal stress, and I'm going to equate normal stress here to the hardness that an asperity exhibits. Now the hardness of ice is a function of the time on which ice is pushed against itself. The greater the time, the lower the hardness, the greater the contact area. It's a function as well of temperature. And so we invoke here expressions Barnes, Tabor, and Walker gave us so many years ago. For the creep rate, I'll just take it out and reverse the expression for the shear strength. I'll take the hardness and again take it out separately from the way they had done it. And I'll talk about the time of contact of an asperity in terms of the asperity diameter divided by the velocity of sliding to get a number. And putting that together gives us an expression for the coefficient of friction. Once again, we need parameters for the asperities. We've never measured, no one's measured the creep parameter of a tiny 30 micrometer size type asperity. So we have to, again, one more time, use parameters measured from bulk materials. And so we take those parameters and we look at 1 point. 1 point, 10 to the minus, I can't read that, 10 to the minus 6 is that, perhaps? Whatever, it's the lower range on our sliding speed, and ask, what does the model predict about the coefficient of friction under that specific sliding speed at minus 10 centigrade? And if you put some parameters to work and take as the deformation zone 100 micrometers, as Barnes, Tabor, and Walker taught us, then you end up with an expression that says, okay, at 10 to the minus 7 per second, the model, we have the shear strength of 4.2 megapascals, the hardness taking for their 300 seconds of about 15 megapascals, a coefficient of 0.28. That's the 0 here. The measurement under those conditions is 0.33 plus or minus 0.05. You say that's not bad. If you ask, what about the effective velocity? Well, here we are. The next two other velocities, higher by each an order of magnitude than the former one. Using that same deformation zone of 100 micrometers, we find that it's not quite good. We're down a bit in the calculation. But I don't know how good is 100 micrometers in terms of the deformation zone. Perhaps 50 micrometers might work. So if you change the deformation zone, reduce it by a factor of 2 to 50 micrometers, oops, I'm sorry, that's 100 micrometers. But if you change it by a factor of 2, you get somewhat better agreement. The point is here that the velocity strengthening regime can be understood, at least at some level, through just creep deformation of asperities. What about velocity weakening? It's a different story. Now we evoke, again, bring into the story the idea of localized melting. For now, we will say at higher velocities, again in the low speed regime, the heat generated through frictional sliding, through the work of friction, it now has less time to be conducted away from the point of contact. Therefore, more heat can build and a potential exists for localized melting. The higher the speed, more localized melting. So let's imagine what we have here then is a kinetic coefficient of friction that's made up of the coefficient of friction of a dry asperity multiplied by the fraction of the asperities that are dry. Eta is just the fraction of the asperities that are in contact that have melted, plus the coefficient of friction of just water multiplied by the fraction of the asperities which are water. And we take that coefficient of water, although it's non-zero, I just let it to be 0 here for this argument, take it out, and deal only with the first term. And so the question is, how do you measure this fraction of asperities that have melted? I don't know. We've never done it. But if we do an energy balance, we might get some idea about what that fraction is. And so what you have here is just that. The work of friction is being equated to the heat to warm the asperities to the melting point, some conduction away as you're warming, plus the heat of fusion. And so if you put that together, the work of friction here is sensible heat, here is the heat required conduction away, and here is the latent heat of fusion. And put that together and talk about the normal force that's acting on the asperities, just the total number of asperities, times the hardness, times the area of contact. Then you balance forces that way. And then one more time, if you let the time of contact be related to the size of the asperity and to the velocity, and make some assumptions about the thermal gradient in terms of the thermal conductivity of the material, then you end up with a relationship for this fraction of the asperities that have melted in terms of the parameters of the problem, including the velocity of sliding. And so this is what one gets. This is the first order crack at the problem. What you see here then is the blue curve is the theory, putting again one more time parameters that one measures from bulk material, assuming that, well, they're the only numbers we have, and so we use them, assuming they apply to the asperity. And you see here then that there are these regimes, one more time. The dry regime, this model applies not to the dry regime, only to the dry come wet regime. The dry regime are the points I talked about a moment ago in terms of static or I'm sorry, in terms of frictional strengthening. And I just put those stars on here to indicate where the curve was. Here are the measurements, say, under the, what I call regime dry to wet. And the, oops, here we are. And the calculation then is the calculation then are these points here. So you see, there's reasonable agreement at the higher speeds, not so good down here. Not quite sure why that is. Maybe there's more to the physics here than we fully appreciate. But at least to a first approximation, one might conclude that there's reasonable agreement, certainly not perfect, between this rather simple model and the observation on velocity weakening. So with that, I'll draw conclusions. First, the coefficient of static friction of sea ice increases with hold time under load by as much as a factor of 3. Secondly, at low sliding speeds, the coefficient of kinetic friction varies by as much as a factor of 10, maybe more. First increasing with velocity, then decreasing with velocity. What that implies from an Arctic field predictor is that sliding is stable at lower speeds, then becomes unstable at higher speeds. As the wind picks up, unstable sliding. And finally, the mechanisms underlying static and the low-speed kinetic friction of ice can be understood at some level in terms of creep, fracture, and at higher speeds, localized melting of asperities. So thank you for your attention.
We have 15 minutes for questions, please. Question, discussion, so then anybody would like to start? Yeah, please then.
Thank you, Alan, for a fantastic talk. At the beginning, you talked about the large-scale deformation features in the sea ice cover, unique kinematic features, and you suggested that they looked vaguely Coulombic, and I agree with you. Okay. But the intersection angle of those features should depend upon the effective coefficient of friction. Now, you just said that the coefficient of friction can vary by quite a large factor. Okay. But these are under lab conditions.
Correct.
So in physical conditions, the range may be less.
Indeed.
Is it possible to compare
Yes,
the range
again.
of observed intersection angles in the field with what you predict from this?
It is, Danny. I showed you in that second or third image, I forget, a set of intersecting features which we call intersecting Coulombic shear faults. And the angle there was, I forget, but from that angle deduced a value of the coefficient of friction of 0.9. And I've just spent some time telling you that the coefficient of kinetic friction varies. So surely that angle, if what I said is true, must vary. And it does. If you look at papers by Marco and Thompson back in '77, JJR, right up to the recent times, and I wrote a paper in 2004 reporting also a variation of angles. And if you look at a number of these intersecting, and again I call them conjugate faults, out of the rock mechanics literature, for where they're seen as well, that the angle, there's a range of angles. And one can interpret that in a variety of ways, I suppose. But one interpretation is that perhaps these various features are forming under different conditions, maybe under different sliding velocities in which the coefficient would change. Perhaps there's some temperature change. Certainly there's a temperature gradient across the ice. And I would simply have to say, well, within that range of theta values is incorporated a range of coefficients of friction, if you work it out, that embodies the coefficients of friction one measures in the laboratory. I did want to make a point, and I didn't, when I showed you the failure envelopes, that is, the slope of the envelopes measured in the laboratory and deduced from the field. The point of that slide was to give you some hope, or some hope that what one measures on the smaller scale about the coefficient of friction may well be relevant to the larger scale. There's always this question out there whether what one sees in the laboratory has anything to do at all with what's going on in the fields. And you can see some of the reviews of papers we've written saying what you there see in your laboratory has nothing to do with what we see out here in the field. I disagree with that completely. completely. And I hope the idea that at least the slope of those envelopes is one piece of evidence to give you some faith that the coefficient of friction, at least, is one of these parameters that's not dependent upon scale.
Many things, very interesting as usual, of course. I have two questions actually, both related to the transition from static or from stick to slip, let's say. One is, since you have shown very clearly that the static friction is time dependent, do you think it's fair to characterize the kinetic friction as a time independent sort of quantity? Don't you think that it has to be time dependent as well, starting from the transition from stick to slip?
Yes. So the time dependence in the kinetic coefficient, I should think, might be manifested in some way or reflected in the velocity dependence, wouldn't it not?
So.
Sure. But I rather think that during the sliding process, sort of the steady sliding process as well, there's contact, there's creep going on during the sliding. Well, we said that in the model, of course. Yeah, I think it's very, very much time dependent. But there's something else I think about kinetic coefficient that's not often said. I don't think sliding is uniform.
No.
I believe, since we have points of contact, that there's a spatial temporal variability to sliding. And so if we could see the interface, and I don't know how I can do that, but if I could see these points of contact, what I envisage is one might let go at some point in time, its neighbor might build up elastic stresses, and it might let go. And there's a spatial temporal variability here, I think, to the phenomenon. When I use the velocity of sliding in a global sense, I do really mean global, but I think if I could see it on a spatial, point by point, time by time scale, I think it's really quite a lot all over the place, lighting up, stopping, lighting up, stopping. And though we spoke here of a size of asperity, 30 micrometers is what we deduce from the coefficient static. Look, there's going to be a range of sliding sizes, small ones to large ones. And the small ones are going to melt out first, the large ones later. So there's a lot of variation here that goes on, I think. But this is a gross first order model. Got to try something.
Quickly. So then about the second conclusion here, where you say that at low speeds the system is stable, well, as long as it moves, right? Because I guess the kinetic friction at very small speeds is always smaller than the static one, right? So there will be always this stick slip instability at small
Always be
speeds as
stick
well,
slip,
right?
even during the slow sliding where we speak about what I say here, stable sliding. By stable, I mean if your wind is blowing on the Arctic ice cover and the wind is picking up and the velocity therefore is increasing, that up to a certain velocity, it's not going to run away with
I fully
itself.
understand what you mean, as long as the slope is positive.
As long as the slope is positive,
yeah.
even though there's a dynamic instability superimposed upon that
But there
slope.
will be always, right?
Yeah, macroscopically stable. But once we get beyond a critical velocity, things are going to let go. Something's going to become unstable.
Yep.
I guess.
Thank you, Erland. You said two things that I cannot put together. The first one was that the importance of friction to strength. And the second one was that the friction was not affected by salinity of the ice. So one easily makes a conclusion that salinity doesn't affect the strength.
Yes, and it doesn't.
Okay.
If I strength first, strength, compressive strength, as a function of the parameter we always measure, strain rate, yeah, at some temperature. Log strain rate. Ductile behavior, brittle behavior. Ductile behavior creep, brittle behavior fracture. Okay? Within the low speed creep regime, the strength decreases with increasing salinity. Saltwater ice creeps more rapidly than freshwater ice. The higher the salinity, the greater the rate of creep, or for a given rate, the lower the compressive strength. In the brittle regime, at least in the measurements we have done in the laboratory, on complete failure envelopes both triaxial and biaxially loaded ice. We cannot statistically, at least at the conditions investigated, -10, -5, whatever, we cannot distinguish brittle compressive strength of sea ice from freshwater ice. So what it means is then that one comes up here, and so we have freshwater and saltwater ice. The difference is that the transition from ductile to brittle behavior is at a higher rate for the sea ice, and yes, we've measured that, and it is at a higher rate by about an order of magnitude. So that accounts for the absence of an effect of the coefficient of friction, let's say, is consistent. Over here, whether you're dealing with saltwater ice, Yucca, or freshwater ice, coefficient's the same, and the strength is the same. So does that add up now for you?
Yep.
Good. And your second question, or was that it?
No, it was that one.
Both together. Got it.
Can I just follow on from that point? So, yeah, that's right. But the tensile strength depends upon the porosity, and the porosity depends upon the internal salinity.
Oh, indeed. Tensile strength, different story altogether. Yeah, no friction in tensile strength. No, take friction out of the story. It's only fracture toughness and defect size. No friction.
May I ask one more question? That's about the energy balance in thin layers. In last part of your talk, you mentioned that energy balance includes heat energy to heat up asperities up to melt point, then heat up just to count heat which goes into the ice and latent heat. And then it was mentioned in literature. I sent you papers. Then it is not enough. In thin layers, you need to count potential for van der Waals forces. And this potential will depress melt point. So then that's my question, that probably some additional energy should be counted when you consider thin layers, because we may get supercooled water, and it is known. And this information is in the paper Pre-Melted Ice and Geophysical Systems. I invited John Mitlauer, but he didn't participate. So, but I think that could be important.
I think you may well be right, Alexei. As I said, this model I presented is sort of a first cut model. Are we anywhere close to the ballpark? I'm sure there's more physics that has to be put into that model. Pressure melting was in, I didn't point it out to you.
And another question, when you consider micron asperities, so and when you consider sliding over 10 centimeters, so actually each asperity will be under cyclic loading, because distance is small, and when you slide, and creeping cyclic loading is different from quasi-static creep. So maybe it can bring some new physics as well.
If there's any truth in what I said, I think it's valuable to add some of these other dimensions. If there's no truth, just forget about it all.
Very nice talk. Thank you very much. I was just wondering about, so on the local strain rate for these asperities, because they're so small, it actually is quite, I'm not sure what it would be, but I imagine it would be quite high. Just wondering if you've looked at, are there potentially fracture processes and breakup at the interface when you get into higher regimes? Because you can, as the speed increases, I wonder if there is some relationship there with the transition from more ductile or creep-dominated behavior to perhaps some localized breakdown as well, which you would see in the field.
Rocky, I think there may be true. That may be right. When we first saw this kind of behavior rising and then falling, my first thought, oh, that's really rather reflective or reminiscent of the ductile to brittle transition, where we go from creep-driven to fracture-driven behavior. And I tried to invoke a fracture model. I couldn't get it to work. The only model that would come anywhere close to what we're seeing was this one I did with thermodynamics and sort of the mechanics of contact. Fracture, I think, may well be in there, because if you look at the hardness, the hardness comes to quite a high value at these rates. If you put the numbers in and you stand back and say, look, an asperity can't support that much stress, it's got a fracture. So I expect if we listen to this microacoustics, we're going to hear something. So I think fracture might be in there as well. More complexity.
One more question. Erland, you mentioned that failure envelope was constructed for -10. Is there some dependence from temperature?
Oh yes.
So, but then I want to ask you a question the same I asked Danny on another workshop. That the yield surface in large-scale models doesn't depend on temperature. Is it correct?
Well, I don't know enough about that to be able to say to you whether yield surface in large-scale models depends on temperature.
But you showed it.
But in you know, the data I showed you from the field, taken from Jackie Richter, Mengi, and others out there during the Shiba experiment, I don't know what the temperature, the atmospheric temperature was up and down, and the ice probably was very, well, the bottom surface, of course, is -2 centigrade, 1.8. The top is up, and the gradient is probably doing this, if I don't know what's going on. So the whole range of temperatures within the ice. So I expect, you know, any variation one is seeing as a reflection in part. But yes, the envelope does depend on temperature because the parameters in the affecting it depend on temperature. Not so much fracture toughness, but coefficient of friction does.
Oh, we have break. Thank you very much.